Well, hello, I'm back again, and the first part of this DC motor video series, we went in and we talked about permanent magnet motors. Now what we want to do is we want to talk about wound DC motors. Now what I mean by wound, instead of having a permanent magnet to create the field, then what we do is we actually go in and take a coil of wire and we run current through it, and that creates the magnetic field for us. Okay, so let's go back to this drawing here, and we talked about this at the beginning of the last one. And so let's look at this. So first thing we want to look at is we want to look at this right here. So this is the one that looks more closely to the permanent magnet than the others, and what you have is called a shunt. Okay, and so here is the field coil, and it's actually hooked in shunt or parallel with the armature circuit, and this is basically representing the armature circuit. So this includes the armature resistance, includes the armature inductance, and also it includes a counter electromagnetic force or voltage that's produced by the rotation of the armature in the magnetic field produced by this field winding. Okay, so we've got the armature winding here and the field winding here. So this essentially is called a shunt winding, and notice that basically the same voltage that is applied here goes to the armature, part of it, and part of it goes to the field. And this is a large enough resistance here so that it doesn't short out the current going through here. Okay, so more current's actually flowing through here than through the field. Now here's the other connection. This is called a series connection, and so you get the voltage applied through here. In this case, the armature winding is in series with the field winding. Now in this case, the field winding doesn't have as many turns as it does here, and you have a lower resistance. Okay, so this is in series with the armature winding. Now the next connection is combinations of these, and so in this case here you'll notice that you have a shunt winding, shunt field in parallel with the armature, but then you have a series winding coming off of that. This is called the cumulative compound, and this one's called the differential compound. And in this case here, what you have is you have the series winding here in parallel with a winding from here. So keep in mind that when you have series windings, you got fewer turns and less resistance than you do when you have a shunt or a parallel line. So here's a shunt winding, here's a shunt winding, and here's a shunt winding. So series, series, and series, and that's what the S's stand for. Okay, and then there's two others that we're not going to talk about. Okay, let's go and let's talk some equations. So here, wound DC motors instead of permanent magnet motors. We're going to talk about some basic quantities here. Don't worry about this right now, but let's see. We've got the armature current, which flows through the armature. We've got the field current, which flows through the field. We have Kf, motor constant for the field, Ka, a motor constant for the armature. And we also have the counter EMF. This is the voltage, electromagnetic force, or the voltage generated when the armature rotates. When the armature is not rotating, this is zero. But as it increases, then this voltage gets larger. Okay? Now, let's look at torque. Now remember, for the permanent magnet motor, we had the torque was equal to a constant times the armature current. Well, we got the same form here, but in this case here, this constant depends upon the field here produced by the field winding, and so essentially what this ends up being is Kf, okay, the motor constant for the field winding, times the current through the field times the current through the armature. Okay, and then here we have the counter EMF, and before we had Ke times this, but now we've got Ka times Vd. Okay, now this ends up being Kf If times omega m. Now notice that these look very similar, and recall that when you take the torque and you multiply it by the speed, or T omega, then what you end up with is power. So if we multiply this by Wm, we get the power. And notice that this here, if we multiply this by the current through the armature, then we'll get the same thing. Well, what we've done is written that down here, where we've got EA, which is the counter EMF generated in the armature, times the current in the armature. This is the electrical input for a motor. Okay, this is the electrical input power. And then T times omega, torque times omega, we know this is power. Okay, so this is the mechanical torque produced by the motor, and this is the actual speed of the shaft of the motor, okay, or the armature speed. So what we have here is we have input electrical power equals output mechanical power, and that's what a motor does. Okay, all right, let's go to the next slide. Okay, here what we're doing is we're going in and looking at some different curves for different types of connections. Okay, and so these are the motors, and notice that what you have here is you have your torque speed curves, but the things are different than what we had before. Before we had torque on the vertical axis and then speed on the horizontal axis. So let's look at this. So what we have is we have the torque speed for the motor, and if you recall, it would go down to 0 here, and now what we have is we have a load torque. So this is the torque produced by the motor, this is the load torque. And notice here, if you were to turn it on the side, you see that it's almost like a y equals x squared type of thing, okay? Because what's happening is the torque, the load torque of the motor, okay, depends upon the square of the speed, okay? And so that's why it's like a quadratic thing. Well, anyway, at the point at which these intersect, that gives you the torque that the motor's producing, the torque that the load, the fan, is dissipating, okay? And then here is the resultant speed right in this point here, okay? So this here is pretty close to what the permanent magnet, and is probably the permanent magnet type torque speed is what you have. Although when we drew it all the way down. It looked like a triangle, you know, when you drew it all the way down. Now here, what we have is we have, for different connections, we have a series connection, we have the shunt connection, which is similar to this, and then we have the compound connection, okay? Now notice also that along here we have load torque in percent of rating. So 100 here would be the maximum, the actual rating, the working torque that the motor is designed for. And then here we have speed in percent of rated speed. So this is the rated speed. So we have the rated speed and the rated torque, okay, at this point here. Now, what's interesting is several things. First, let's look at the shunt. Okay, if your torque goes to 0, if your load torque goes to 0, so if you take the load off, then you'll notice what will happen is you'll go a little bit higher than the rated speed, and then that's it. It won't go any faster. Now, look what happens with the compound. If you basically go in and you reduce the load torque, you take the load off, then it's going to go much higher than the rated speed, okay, for the compound. And then look at the series. If you take the load away from the series, then it's going to go really, 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 really fast. And what's going to happen is probably going to explode. It's just going to go so fast that it's just going to explode. So that's not good. That's telling you that with the compound motor and the shunt motor, you can take the load away. It's just going to go really fast. Okay, but for the series motor, you should never, ever, ever take the load away. It should always be connected to some load before you turn it up. Okay, now let's look what happens when you basically increase the load to higher than the rating. Well, if you increase it higher for the shunt, then essentially it's going to maintain its speed pretty good. And notice that this has got what you call speed regulation is really good, because as your load varies, basically the speed stays pretty much the same of the motor. Now for the compound motor, not so much, you notice that from no speed down to rated speed, basically it changes quite a bit here. And then if your load gets a little bit higher, then it starts dropping really fast. So the compound type gives you a lot more torque. You see here, it's a lot more torque. Well, actually, I mean, it's a lot less speed. I keep getting mixed up with the axis here, but with the compound one, you have something that's a speed that's varying quite a bit, so it's not very good regulation. And then of course the series is varying like crazy. Okay, as the torque of the load changes, it's going there. Now let's look at this on the other side here. If we look at let's see, this is versus load here and speed. Well, no, that's good. So essentially that's the way you should read this, is you just look at the load torque and see how the speed varies, and essentially the shunt, the speed is pretty constant. The compound, not as good as the shunt, but the series, the speed is just going all over the place, and actually you're going to see some damage occurring to the motor if you take the load off. Okay. Okay, so let's go down here and let's look at the equations here. Now this is a motor. We're talking about motors here. So what we have over here is the left side is the actual electrical torque. Okay, and so this is the electrical input torque, and it's in terms of the electrical quantity. So you got the KF, you got the field current, you got the armature current, and then on the right we're talking about mechanical type torque. Okay, so this is the load torque, this is what's dissipating the torque, and then this right here is the torque due to turn the motor. Okay, so the motor has a certain rotational inertia and it's being accelerated by a certain amount, and so these together are the total torque that the electrical energy has to counter. Okay, so the input electrical torque, this is the output mechanical torque. Okay, so the output torque is actually turning the motor and also turning the load. And here what we have is we have the voltage on the field winding equals the resistance of the field times the current of the field. And here we have the voltage applied to the armature equals the resistance of the armature times its current plus KF IF times omega M, which is basically the counter EMF that we talked about earlier. Now over here what we do is we talk about the power division of the motor. So this is the input power coming into the motor. Okay, so we got the terminal voltage times the current going into the motor, and then over here what we have is the actual power that's going to the load, okay, on the shaft. So this is the mechanical output power and this is the mechanical in, and what this does is goes and shows you where the losses are. And so you see here that you have the shunt field copper loss, you have the armature circuit losses, and then you have the rotational losses due to turning. And so if you add these up, worst case, you got 5 and 6 is 11. What is that? 26% of the power being lost from the actual input power. So that gives you what, like 74% efficiency. In other words, output power mechanical to the total input power coming in. So that's not too bad. And then here, if you're looking at the smaller cases, you got 1, 4, 7. So that's what, 93% efficient, you know. So it's a wide range there depending on the losses in the motor. Let's go to the next slide. Okay, now what we're doing is we're doing similar to what we just did in the previous slide, but this time what we're talking about is we're talking about generators. Okay, here notice that what we have is, instead of speed and torque, we have voltage and current. So this is the load torque of whatever you're driving with the motor, with the generator, and actually this is going to be some type of resistance or load. It could be light bulbs, it could be a motor that you're driving. It could be a refrigerator. It could be anything, whatever you're hooking to the generator and using power with. So here we have voltage versus current. Now the generator is rotating, right, and something's rotating it. It could be some type of it could be basically this could be a windmill, or not a windmill, but a wind turbine. It could be a hydroelectric plant. It could be a diesel engine, that basically is going in, or gasoline engine that's actually turning the generator, and that's called the prime mover. Whatever is actually rotating the shaft on the generator, that's the prime mover. So here what we're doing is at a given speed, we're looking at the generator voltage and the resulting current, okay? And as you see, as the current increases, the generator voltage is going down, okay? And so we can see for open circuit, if the current increases, then the voltage goes down, down, down until you end up with this. Now, here's the thing, is this is the open circuit, or not the open circuit, but this is the curve that you get by varying the output current. And in this case here, zero current to max current. But you're going to have a circuit, which could be resistances, it could be motors or other stuff, and basically it follows a characteristic like this. So basically the voltage on the load and the current on the load is given by this curve here. Now where these two intersect is the operating conditions. So for this particular load, what you have is you have this much current flowing and this much voltage at the output, okay? And later on in the course, when we talk about batteries, we'll talk about something similar here, okay? So this is a different kind of curve when we're talking about generators. And then over here, what we've got is the same kind of thing, but now we're talking about the different types of generator connections. We got the series connection, where the field winding and the armature winding are in series, right? And then we've got the shunt, where the field winding and the armature in parallel. And here, where the shunt, basically what's happening is both the same voltage, or the winding for the field and the winding for the armature are actually electrically connected. Now, for separately connected, this means that the actual field winding has its own separate source hooked up to it, okay? But for the shunt, basically they're tied together. And then you got the compound here. So let's look at some of these. So let's look at the series first. So if we look at the series, okay, this is 100% the rating, the percent rating of this generator for current, and this is the rating for voltage, 100%. So at this point here, you're operating at rated voltage and current. Now, notice what happens here is that for the series generator, with zero current being drawn, you got zero voltage output, which seems kind of weird until you actually look at the circuit. And then as your current increases, the voltage increases, and then your current's increasing more until you reach the rated voltage. So for this particular situation, if you change your load current, then your voltage is going to drop quite a bit. Look at there. Look at how fast it's dropping. So with the series circuit, you need to have it set up and running, with the particular load current that you're going to use, because down in here, it's going to be way low voltage. Let's look at the compound type connection. And so the compound is this one right here, I believe. Let's see, was it a dot? And yep, that one there. Notice that with no load applied, or open circuit, that you're getting what, maybe about 85, 80% of the rated voltage coming out. And as your current increases, then it stays fairly level. Okay, so not too bad. Now let's look at the separately excited. Well, look at here. The output voltage is staying fairly constant over the entire range of current here. So that's pretty good. And then the shunt is a higher voltage here, and then it's coming down and changing quite a bit. And actually the shunt is changing the most, notice that when you go in and you increase your current load, you draw more current than it's rated for, that this voltage drops off pretty quick. And this is what, about 75%? Whereas the compound motor, essentially here, it looks like it's staying pretty good, even for exceeding the rating of the motor there. The separately excited is not too bad too. And look at the series. Now this is what seems weird at first, but when you go in and exceed the rating of the generator, it actually goes in and increases the voltage. None of the others do that. So that's interesting. Now let's look at the equations here. Now we're talking about generators here. So we've got our prime mover. Okay, this is the driving torque, the mechanical. This could be like a wind turbine, or it could be like a hydroelectric plant, or whatever, a diesel engine, gasoline engine driving it. So this is the input mechanical power, and here's the output power. Now notice that this right here is the mechanical torque of the motor, okay, because the motor's heavy and you have to rotate it. Here's the rotational inertia of the motor, here's the acceleration, okay. So this is mechanical, this is mechanical, but this right here is purely electrical, right? This is the output voltage and current that actually it's a torque, but this is equating to the output electrical of the motor, okay? So you got mechanical in, you got mechanical dissipating because you have to turn the motor and stuff, and then this right here is corresponding to the armature current and the field current, and this right here is a torque, is an output electrical torque, but this is representing the torque that's produced by the current that's flowing on the output. Okay, so if you don't have any armature current flowing, which means that you don't have anything hooked to the generator, nothing's dissipating energy, then this goes away. Okay, but this is still going to be there. Okay, and it's interesting because if you take a generator and you go in and you increase the current coming out, then the speed will basically drop, because unless you increase the mechanical driving torque. Okay, so and here's the equations here. The voltage across the armature circuit is KF IFWM. Okay, so this is the counter EMF we were talking about before, minus the drop due to the resistance of the armature and the current. And then the voltage across the field is equal to this. Okay? Now let's look at the losses here. So you got the input power from the prime mover, okay? And then you got the output power that's actually being used to power devices and appliances and stuff. Okay? And so you got rotational losses, armature circuit losses, shunt field losses. So let's look at worst case again. So here you got 15, 20, 26% is about what we said before. Best case, 3, 6, 7%, about what we said before. Okay, so you're getting a pretty good deal here as far as efficiency. What, from 74 to like 90 something percent efficiency. When you look at, in this case, output electrical power divided by input mechanical power. Okay, and it was the opposite, for the motors, but this is for the generators. Okay, let's go to the next page. Okay, here what we have is a compound motor. Okay, it actually goes in and shows the current flowing for different situations. If you have a generator, then actually you got current coming out of the armature circuit, and actually part of that current is used to drive the field windings. Okay, you got series field in this. And then if you're talking about, and so you got an output voltage, so it's mechanical to electrical. And if you're talking about a motor, then here this is have the voltage that's input, and the current's flowing here going into this, and the actual armature current flowing into here is what's creating the mechanical power coming out. Okay, And here what we do is we're actually showing two cases. This is for a motor and this is for a generator. And here again for the motor, you know, it's actually the electrical coming in, going in here and going in here is what's causing this to rotate. And for the generator, what we have is a prime mover is rotating the shaft, which is basically going in and generating the output voltage here, assuming that if it's separately excited, then you've got some other source doing this. Otherwise, these are connected together. Okay. And here, essentially what we have is we have basically a summary of the equations here. Here again, we have the equation for the armature circuit. And here we have an extra term. We ignored this before because in the steady state, you know, we don't have to worry too much about this. But during transient turn on and stuff, you need to consider this. And so this is the armature resistance times the current flowing through there. This is the counter EMF that's generated. And then this is a term due to the inductance of the armature. So this is the electrical equation, the input for the DC motor. And then this is the torque generated equals KT times IA, right? We said that before. And then this is all mechanical. So here what we have is we have the rotational inertia of the motor plus the rotational inertia of the load times acceleration. This is basically a torque that opposes what's generated. And then what we have is the torque created by the load here and the torque created by the motor. Okay? And so I won't go through here. We've already talked about this before. So let's go to the next page. Okay, now we've been talking about rotational inertia, and so let's end this part 2 by actually looking at some equations here. And so this came from a really old physics book I used to have. I still got it somewhere. The shape that more closely looks like a motor is a solid cylinder about an axis. So this looks like the armature, okay? Now it's not going to be perfectly round. It's going to have like slots and it's going to have coils of wire and stuff like that through there. But as you can see, the rotational inertia here is the mass of this cylinder times the radius of this cylinder squared divided by 2. Okay, so that's what we're talking about when we're talking about the rotational inertia that we saw in this equation here. Okay, for the motor. That's for the motor. And you would do the same thing for the load. If we go back here and let's say that we had annular ring, or say we had something like a sphere or some other shape, then you could calculate that and plug that into your equations here, and you could actually go in and figure out the actual speed or the torque produced. Once you know the torque produced, which is KT times IA, and you know what the rotational inertia of the load is and of the motor, then you could actually go in and do calculations to figure out what the acceleration was and what the final speed would be. So these are the two equations that govern the whole operation of the motor. Okay? All right. Well, the next is going to part 3 of this is going to be talking about gears and some more about different types of load torques. So let's stop right here. This is the end of part 2.